Today we're going to talk about the three types of radiation that occur because of radioactive decay. It's alpha, beta, and gamma radiation. Now it turns out that some nuclei are unstable. And so these nuclei, they basically fire out particles and become more stable. Sometimes this can be a very complex process, sometimes it's a very simple process. Some nuclei go through long decay chains where lots of particles, lots of different types of particles will be emitted. Others go through a very simple process. But there's only 4 types of particles that are emitted. The first of those particles are called the alpha particles. We use the Greek letter alpha to represent those alpha particles, but what they are really is helium nuclei. So a helium nuclei has 2 protons in it and 2 neutrons, so it's got a mass number of 4. If it's a nuclei, that means the electrons have been ripped off the atom. That means it's going to have a charge of whatever the charge of the nucleus is, which is that charge number there, plus 2. So all these alpha particles have a mass of 4 and a charge of plus 2. The second type of particle is called the beta particle. And here's the Greek letter beta. Now beta particles are really just electrons, so they're nothing new to us. When the electrons are emitted in radioactive decay, we call them beta particles. So you might see a symbol like this. There's the beta particle. Beta particle has a charge of -1, so we put a -1 here for the charge number. But it's essentially got 0 mass. At least compared to a nucleon, it's got 0 mass. So this here would be another representation for an electron. Now it turns out there's an anti-electron that's sometimes emitted. An antiparticle has exactly the same mass, but it's got the opposite charge. So this here would be a antiparticle. In this particular case, it's called a positron. So we'll talk more about positrons later. For now, just think of them as a type of beta particle. Now, sometimes something called a neutrino is emitted, and we usually give it this Greek letter here. These neutrinos are very, very hard to detect. In fact, they were predicted about 30 years before they were actually detected. And the reason they're so hard to detect is that they don't have any charge and they have almost no mass. They just pass through the universe like it wasn't even there. And it turns out antineutrinos are also produced. Last but not least are the gamma rays. The gamma rays are just they're part of the electromagnetic spectrum. You can think of them as energetic photons. And they occur when a nucleus de-excites. So we talked about atoms getting into excited states. Well, a nucleus can get into an excited state as well. And when it falls back to a lower energy state, it can release one of these gamma photons. Now I was saying earlier that the neutrino essentially doesn't interact with matter because it doesn't have any mass and it doesn't have any charge. And that's why it took so long to detect the neutrino. So what we're going to do now is compare the alpha, beta, and gamma particles in terms of mass and charge in order to predict which one of them is going to interact the most with matter. So if we consider the mass of the beta particle, let's give the mass of the beta particle a mass of 1. So it's in units of electron masses. Then the alpha particle is going to have a mass somewhere around 8,000 times as much. And a gamma particle is essentially going to have a mass of 0 because it's pure energy, it doesn't have any mass. In terms of charge, the alpha particle has 2 protons in it, so it's got a charge of plus 2. The beta particle has a charge of -1, and of course the gamma particle doesn't have any charge at all. So if we predict which one's going to interact the most with matter, of course it's going to be the strongest interaction by far with the alpha particle. The beta particle is going to have a fairly weak interaction with matter, and the gamma particle would have a very weak interaction with matter. Now you might be asking yourselves, if we included the neutrino here, it would also have a mass of 0 and a charge of 0. It has essentially no interaction at all. So why is the interaction of the gamma ray a lot stronger than that of the neutrino? That's because gamma rays are electromagnetic radiation. They're oscillations of electric and magnetic fields, and of course the electric and magnetic fields can interact with matter. Now, if the alpha particle has a lot of interaction with matter, that means it's going to give up its energy. And that means it won't be able to penetrate through different substances as well as the beta particles or the gamma rays. In fact, an alpha particle won't even penetrate through a sheet of paper. Beta particle quite easily penetrates through paper, but couldn't get through, say, some aluminum foil. And a gamma particle, it can make it through the aluminum foil. And in fact, you would need a thick piece of lead in order to stop a gamma ray. It has very little interaction with matter, so it penetrates through matter quite easily. So the alpha particles might be able to get through a thin sheet of paper, and they could make it through about 4 centimeters of air typically. And of course it depends on how much kinetic energy those alpha particles have originally, how far it can penetrate. The beta particles, generally they're going to be stopped by aluminum foil or tin foil. They could make it through about 1 to 3 meters of air. Once again, it's going to depend on their initial kinetic energy. The gamma particles, as I said, you need a thick piece of lead to stop a gamma particle, several centimeters in thickness. And the neutrinos, they'll pass through anything. Now, closely related to the ability to penetrate is the ability to ionize. The alpha particles have lots of charge, and they can just pass by an air molecule and rip some electrons off. So they can cause a lot of ionizations. They don't penetrate very far, but while they are penetrating, they cause a lot of ionization. The beta particle, not nearly so good at causing ionization. It has to collide with those molecules in order to deliver enough energy to knock an electron off. The gamma particles, even less ability to ionize. Once again, the gamma particles have to make quite direct collisions to deliver their energy and remove an electron. And the neutrinos have never been known to cause an ionization. The way that we typically separate the alpha particles from the gamma rays from the beta particles is by using magnetic fields. Because of course the gamma particles have no charge and are not affected by the magnetic field. The alpha particles are positively charged and the beta particles are negatively charged, so of course they're going to twist in opposite directions. And the other difference, of course, is that the mass of the alpha particle is about 8,000 times as much as the beta particle. So the radius of curvature here is going to be much larger for the alpha particle than it is for the beta particle. Keep in mind that radioactive decay is not something exotic or rare. Radioactive decay is happening around us all the time. In fact, if we got a Geiger counter, which is used to measure radioactive decay, it would show significant detections of these decay particles. And we refer to that radioactive decay that's around us all the time, we refer to that as the background radiation. And we want that background radiation to be low enough that it's safe for us. Let's review with a few IB questions. So pause the video, try the question, come back for the answer. So why do alpha particles only travel such a short distance in air? A, because they undergo radioactive decay. No, alpha particles are very, very stable. They do not undergo radioactive decay. B, they undergo elastic collisions with air molecules. Well, that sounds kind of right, but beta particles do that as well. So it's not a great answer. Let's look at D now. They are attracted by the nuclei of air molecules. No, because alpha particles are positive and the nuclei are also positive, so they actually have a repulsive force between them. So that's not the right answer. The correct answer is C. They ionize the air molecules. So as the alpha particles are passing by, they rip these outer shell electrons off the air molecules. And of course, that's going to cause a backwards force on the alpha particle. And that's going to slow it down greatly. So the correct answer here is C. Question 2. Pause the video, try the question, come back for the answer. So which of these determines the range of the alpha particles? Well, definitely the density of the air. The air molecules are blocking the passage of those alpha particles. Definitely the kinetic energy of the alpha particles. If they've got more energy, they've got more energy to lose, and they're going to penetrate farther. And 1 here, the charge of an alpha particle, well, you might say no, because all alpha particles have the same charge. But on the other hand, charge definitely affects the ability of particles to penetrate farther. So we're not sure about that one. There is no answer down here that says just 2 and 3. Therefore, the best answer, the correct answer, is going to be D. 1, 2, and 3 are all true. Question 3. Pause the video, try the question, come back for the answer. The graph here is basically saying that all of these alpha particles are penetrating the same distance. Now that's only going to be possible if they've all got about the same initial kinetic energy. If they had higher kinetic energy, they would penetrate farther. So the correct answer here is A. These other statements might be true. So for instance, B is true. The range is independent of the initial energy. But there's nothing in our graph that tells us that. C is also true, but it's not from the graph. D is sort of true, but once again, you can't tell that from the graph. So let's summarize. We started by talking about these alpha particles, but they were really helium nuclei with a charge of +2. We then talked about the beta particles, which were really electrons with a charge of -1 and essentially no mass. Turns out there was also an antimatter version of this called a positron with a positive charge and 0 mass. We had the neutrinos, which basically had no interaction with matter. And we had the gamma particles, which were just energetic photons. Alpha particles interacted very strongly with matter because they had lots of mass and lots of charge. They could penetrate, say, paper, but they couldn't penetrate very far because they caused lots of ionization. The beta particles could penetrate through foil, and they caused some ionization, but not nearly as much as the alpha particles. Neutrinos, kind of boring because they just penetrate through everything. And then these gamma particles would require centimeters of lead in order to bring them to a stop. And they would cause a little bit of ionization. And that's all for today, folks. Thank you very much.